Okay, question 4. The work done by an external force to move a negative charge from point A to point B is this many joules. If the charge started from rest and at this much kinetic energy when it reached point B, so in other words the change in kinetic energy is positive and equal to this value, what must be the potential difference between A and B? Right. Now this is a good example of a problem where we most likely won't know right from the start how to proceed. So a good way to start is by writing down everything that we do know. So I've got my point A, I've got another point B, and I've got the charge moving from point A to point B. It's a charge Q of minus 8.50 times 10 to the minus 6 coulombs. And what else am I given? I'm given the external work done by external force, which is 15.0 times 10 to the minus 4 joules. And I've got change in kinetic energy, and that's given as 4.82 times 10 to the minus 4 joules. Right, and okay, so what else? Let's write down the formula that we'll probably end up using. Change in potential energy, electric potential energy is equal to Q VBA, and this is equal to minus the work done by the electric field on the force, on the charge. Right. So what am I after? I'm after the potential difference between A and B. So I'm after this VBA term. How can I get that? Well, if I have the potential energy, I can get it. Do I have that? I've got a change in kinetic energy. So isn't the change in potential energy perhaps minus the change in kinetic energy? Well, it would be if only conservative force worked in, but now I've got this bothersome external force working in, so I can't go that route. But how about from this direction? If I have the work done by the electric field on the charge, how about that? Do I have that? Well, I've got the work done by external force. I'm after the work done by the electric field on the charge. Only other thing I'm given is also the change in kinetic energy. And now I'm thinking in terms of kinetic energy, change in kinetic energy, work done. One formula should immediately pop into your head, and that is that the change in kinetic energy is equal to the net work done. Or in other words, in this case, the work done by the external force plus the work done by the whatever electric field there might be. Okay. But how do we write down the work done by the electric field on the charge? What is our notation for that? That is what we write as WBA in this equation, the work done by the electric field on the charge in going from A to B. Okay. Look, but this is good progress. I've got that. That's provided by the question, so then I can work out that. And if I've got that, I can plug it into this equation and find the potential difference. Great. So that's quite simple. So let's do that. First, let's write down what is WBA. That's change in kinetic energy minus work done by the external force. Okay. Now for this, VBA is equal to minus the work done over Q. Okay. What is minus WBA? So that's minus that. So it's going to be work done by the external force minus kinetic energy change over Q. Okay, so let's substitute everything. See, now I substitute now that I have my final expression for what I'm after. Okay, so that is 15.0 times 10 to the minus 4 joules minus 4.82 times 10 to the minus 4 joules over the charge, minus 8.50 times 10 to the minus 6 coulombs. Great. So let's calculate that. Okay, so I have 10 to the minus 4 terms on top. Okay, so I'm going to say it's 15 of them minus 4.82 of them, and then divide by 8.5. Okay, and times 10 to the what? I've got minus 4 on top and 6. So it's minus 4 minus 6, so that's plus 6. So the answer is 2 power 2. I didn't type in this minus, so the answer is minus that. So everything to 3 significant figures, so I'm also going to provide 3 significant figures, minus 120 volts. There we there we go. That's the answer. Okay, so now, lastly, I talked in the tutorial session a bit about how you can anticipate beforehand that this answer should be negative, or how afterwards you can make sense of the fact that this answer works out to be negative. Now this is important. I talked about this in the at the end of the solution to the first problem of this tutorial, in that video. In other words, in the first video for second tutorial. So definitely go and look at that as well. It pertains specifically to whether charge is going in the direction that it wants to go, and for negative positive charges, that means we can determine if it's going from lower to higher potential or from higher to lower potential. Let's perhaps summarize it here. That might be a good idea. So the basic idea is, if you've got a charge Q from A to B, then we talk about the natural way, and or sometimes say it's the charge going the direction that it wants to go. So let's call that the natural way, quote unquote, because it's not an official terminology, and that just means it is when it's going in a direction where the potential and its potential energy decreases. So that would be the same as saying it's natural for a rock to drop down to the earth, or for an apple to fall from a tree. It's going in the direction that the gravitational force is pulling it. So in the exact same way, we consider it to be charge to be going in the natural direction, the direction that it wants to go, if it's going directly in the direction that the electric force is pulling or pushing it in. Okay, so if it's going in the natural direction, which means change potential energy is negative, then if it's a negative charge, or okay, let's do a positive charge first. If it's a positive charge, then it goes from higher potential to lower potential. This is if Q is positive, if it's a positive charge, that is VBA, which is the difference between the two. If this one is larger, is smaller than that one, then that means VBA is negative. But it's the other way around if Q is negative. If it's a negative charge, it goes to higher potential from lower potential. In other words, then VBA is positive. Now this is what was discussed, how specifically these inequalities come about. Specifically how these inequalities come about was discussed in that first video of this tutorial. And this is a shorthand notation for this at the top of the lecture notes on electric potential, at the top of the second page. That's the explanation for this. As a converse to this, a forced way, so by analogy of gravity and a rock, that would be if you're throwing a rock upwards, or you're carrying it up the stairs or whatever. If the change in potential energy is positive, then the whole situation flips. So if it's a positive charge, then the potential at A will now be less than the potential at B. Everything just flips. And if it's a negative charge, then it's a higher potential to lower potential. Okay, so this is pretty much a diagram for the entire situation. So, and a way to understand that this works out to be minus 120, minus a negative number, is to now try and think of, in terms of, is the charge going in the natural or in the natural direction, the direction it wants to go, or whether it's been forced to go in the direction that against the direction which it feels an electric force. So how I can figure that out, or how intuitively I can reason about that, is by looking at these two values. I've got the work done by external force, it's that much for it, and I've got the change in kinetic energy, which is the kinetic energy it ends up with, because it starts from rest. Okay, so it starts from rest, and after it reaches point B, it's got this much kinetic energy. But the work done by the external force is much more. Now, how can the work done by the external force be much more than the kinetic energy that it ends up with? Well, this tells me that this work is done against something. It's done against the electric force. If there was no electric force, or if the electric force was incredibly weak or negligible, so if there were effectively no other force except for the external force that did this work, then if it starts from rest, then this value 15, this is how much kinetic energy it would have ended up with. But it didn't. It only ended up with this much. So this work was done against something. The electric force was doing work in the opposite direction. So this tells me that this charge is not going the direction that it wants to go based on the direction in which it feels an electric force. So it is the forced case. Now for a negative charge, if it goes, if it's being forced in a certain direction, it means its electric potential energy is increasing, then point A, where it starts from, is at a higher potential than where it ends up with. So then, is this right now? Why this is... Oh, big mistake. I didn't flip these, sorry. Okay, is this right? Yeah, this is right, okay. If it's being forced, then the potential A, where it starts from, versus is larger than where it ends up with. So then the change potential and the potential is negative. So sorry, this would be less than 0. It's easy to get mixed up. Opposite of here, right. So by comparing these two values, I reason that this is negative. I reason that this charge is not going in the direction that it wants to go. It's being forced against it to go in a direction against the direction which it feels a force from the electric field that it's in. So it's negative charge being forced in a certain direction, so then the change in potential will be negative. So it makes sense that it is going from that this change in potential, that this potential difference is negative. Okay. Another way you can think about this, and I just thought of it intuitively in terms of, the work of the one is done by the external force is greater than the change in kinetic energy, and that intuitively means it's working against something. I mean, you can think of that. You can visually think of that in terms of a rock being thrown from a building. Let's say you've got the building here, you're standing here, and you're dropping a rock. Okay, and you're dropping a rock from point A to down to point B at the ground, and there goes the rock, it's flying, and you're throwing it downwards. Okay, now let's say initially you're not dropping it, initially you're not throwing it downwards, you're just dropping it, and let's say in the case that you drop it, it gains 10 joules of energy. So it has zeros there, and then when it comes here, it's got 10 joules of kinetic energy. So change kinetic energy is then positive 10 joules. Right, now you run down and you go up again. You run down, you collect the rock, and you go up again. But this time you throw the rock down. So it still starts from rest, but when it leaves your hand, it has got the starting velocity now. But let's say in throwing it down, because you did work on it, and let's say, for argument's sake, you did 5 joules of work on it. Okay. Then if you did 5 joules of work on it, and then how much kinetic energy would it have when it comes down here? It would have the 5 that you gave it by doing work on it in the direction that it's going, plus then the 10 joules it gets just from the force of gravity in the direction that it's going. So it would have 15 joules of kinetic energy at the bottom. 15, but only 5 of those are due to you. The rest are due to gravity. So the work done by you, the external force, is less than the total change in kinetic energy. The opposite case from here. So this would be the natural way for a rock to follow. This would, by our definition, this would be the natural direction for the rock, which we can see illustrated here in the work being done by you, going from A to B to be less than the total change kinetic energy. If instead you're throwing the rock upwards, let's say an arc like that, and you make point B over there at the top, then you're not working with gravity anymore like you did when you threw it downwards. Now you're working against gravity. Now if you give the rock, you throw very hard and you give it and you do like 15 joules of work on it, then all 15 of those joules won't go to the kinetic energy. The same way the 5 joules here, all of it went towards the kinetic energy. No, part of that 15 you're doing it on it would have to be to counteract gravity. In that case, the kinetic energy it would have here would be less, much less than the work you did on it to get it up to that height at a certain speed. So then that would be like this case, where the work done by you is less, is much more than the kinetic energy it has at that point. So this would be a way to visualize it, that work being more than a change in kinetic energy amounts to for a particle starting at rest amounts to it not going in a natural direction, it going in a forced direction like this, per our definition, direction which the potential energy is increasing. Okay, and then it makes sense for a negative charge for the potential to be zero, to be negative. And again, if you want to see where this comes from, this is explained in more detail in the first video, tutorial 2. Okay.